Hello, my name is Wim Bouwman. I'm one of your teachers classical mechanics, and what I want to do with you today is I want to treat with you the problem of three identical masses that are connected by identical springs. So all masses have mass m and a spring constant k. And before we start with the detailed calculations, I want for you to have a break and think about solutions before we go into the real details, where you can calculate the real answers. But you can already get an indication if you use common sense, and it's a very good strategy. So please think now first. I give one hint away. It's very good to take coordinates that are easy to use. And very easy coordinates that are the translations along the circle. And then you have to choose what is the direction, also for the movements of particle 2 and 3. It's nice to use the symmetry of the problem, and for that reason I've chosen them to point also clockwise. And you will see, if you have the circular symmetry, that all the equations get also the same symmetry. So please now, as a first thing, write down the kinetic energy of this system. It's rather easy. It's nothing else than just the movement, for example here of particle 1 squared, the velocity squared, times the mass divided by 2. You have to do the same thing for the other two masses, and you get this equation. Now the second one is a little bit more interesting, and that's where the circular symmetry becomes important. Please write down the potential energy, but only using the second order terms. Well, if we first look at the first spring, then it is the distance between the two that comes into the equations, and you have of course a rest length, but you can ignore it because it will drop out later if you want to calculate the K matrix. So this is the distance between particle 1 and particle 2 from their rest position, and you have to do the same thing for this spring and for this spring. And then you get this very nice circular symmetry that you all follow up. And the last term, then you have it with also the sign in a way reversed. So that's nice. From these two equations, you can now calculate the K matrix and the M matrix. And first, let's calculate the first derivative of the potential energy with respect to the coordinate x1. Please give the equation for it. If you do it, it's just a matter of working out in a simple way. You see the x1 is coming in the first term and in the last term. Here is a negative sign. So that's how you end up with this. Now you can use this equation if you take again the partial derivative with respect to x1, x2 and x3 to get the first row of the K matrix. Please calculate the first row of the K matrix. It's quite easy. As you can see, the x1 is coming in here with positive sign, and here also with positive sign. If you look at the derivative with respect to x2, you only see it here with a negative sign, and with respect to x3 here also with a negative sign. Now once you've got this, you can use the circular symmetry, and the other rows, they are just shifted by 1. Here you see it. Now the final question before you start with the real analysis: what is the M matrix? Please give the first row of the M matrix. It is very simple. It's just a diagonal matrix because you see only terms squared of the coordinate with respect to the velocities of the three coordinates. So that's an easy one. And again, you see this diagonal symmetry, which will make the mathematics much more easy. Now that we have these two matrices, we have to calculate the eigenvectors and the frequencies. Now, a good approach to do this, that is to get this matrix. This is the problem we want to solve in the end. Now, the way to get the values for omega, you can calculate them by putting the determinant equal to 0. What are the solutions that you get for omega of this equation? To calculate it, we worked out, first we look at the first row, and it's quite easy, just please do it yourself. And the other rows, they're easy, everything's again shifted by 1 due to the nice symmetry. This makes it also more easy to calculate now the determinant. First we take the diagonal, and since we have 3 times the same term, this cube, then we take a look at the off diagonals. First let's take the blue one. You see that it's the same as the other one, blue one. So you get here twice minus k to the third. Then we have to look for the determinant at the other diagonal. There you see it, indicated in purple. And now what you see is this one has the same value as, for example, this diagonal and this diagonal. So we get 3 times this term. Now, if you look at this equation, then you can see that the term k will drop out. They're equal. Here you got power 8. This is minus 2 and this is minus 6. So we got rid of that. That makes it more easy. And if you take a look at what we have left over, you see the whole time everything's going by omega squared m. So there we have one solution already. That should be 0. And then if you look, then here we get a squared term in this term. So that gives us the solutions we need. One of them is omega squared is 0. And the other one is twice omega squared is 3k over m. Now, we have to interpret these solutions and we have to find the eigenvectors. Please give first the eigenvector corresponding to omega squared is 0. If you do that, you can fill in the omega squared is 0 into the equation here. And then you have to solve for a. And if you do it, you immediately see, jumps to the eye, one solution is all of them have the same value. Well, to which vibration does this eigenmode correspond? All 3 particles move the same direction. So it's like this. It's just nothing else than the rotation of the whole spring system, and there's no vibration connected to it. And that was something you could easily think of beforehand, and I hope you thought already of it beforehand. Now we have to look at the other 2 solutions. Please give 2 modes that are, for example, solutions of that equation. If you fill in this value into this equation, then you get the following equation for the eigenvector. Now you can think of 2 solutions. It's always nice to make one of them equal to 0. If you that have, then the other 2 become antisymmetric. So this is for example, a solution. This one corresponds with this one standing still, and the other two, one moving this way, the other one that way, the anti-symmetric vibration. Now, instead of putting the first one equal to 0, you can also take, for example, the second one equal to 0, and then the other one too have to be anti-symmetric. That corresponds to this movement indicated here in purple. These three eigenmodes, they constitute together a whole set of solutions that you can have for this problem. And I really like the symmetry, and I hope you will try to look in future again for symmetry in problems, because that will make the mathematics much more easy.